It's like also the first day of classes, so people like optimistic and like, you know,
I won 10
bring in and they first
How did you read?
That's good.
Yeah, my sister won
There you go. Good. How are you? How do you start? How do you say you can start?
Yeah, exactly.
Okay, I guess we fan out. We gotta make a path for Andy. Alright, this is CMU 15721, Database Systems. It's raw. Prepare yourself. Here comes the East Coast overdose of databases, the ODB of DBAs, a man that has more SQL than the Pope, the Dalai Lama, and Jose Canseco. Give it up for Andy Pablo!
So welcome to 15721 Database Systems. All right, make sure everyone's in the right place. All right, before we get started, I always like to motivate why you should take this course. I'll also do a little pop quiz here, okay? So let's try to name who the most richest people in the world are, okay? Let's start from the top. Who's the most richest person? Who's the has the most money?
Bill Gates.
Bill Gates, correct. Who's number two? This one's a little bit tougher. He's not in the U.S. Yeah, close, right? Ortega, yes, in Spain, right? The clothing store guy, right? Who's number three? Warren Buffett, right? Who's number four? What's that? Exactly, Carlos Slim, nice work, okay. Number five, now we're getting to U.S. people. Close. He's six. Bezos, right? Six is Zuckerberg. Who's number seven? Oh, Larry Ellison, right? All right, so let's go through this list real quick, okay? 4 out of 7 people here have an interesting database story, right? Bill Gates was the founder of Microsoft, and Microsoft sells SQL Server, and I consider SQL Server to be one of the most state-of-the-art database systems. Jeff Bezos runs AWS and runs Amazon. As far as I know, they're still running Oracle for all of their, like when you purchase things and payments and things like that. But they most famously have RDS and DynamoDB and a bunch of other interesting database systems that they've developed in-house that they sell to customers. Zuckerberg founded Facebook, and they have the installation. They don't give it exact numbers, but we're pretty sure it's the largest. And of course, we have Larry Ellison, lonely here at the bottom, 7. He's had a rough year. He used to be number 5, and now he's dumped down to 7. So Larry Ellison founded the Oracle Corporation. right? Which is the largest database company in the world, right? He's made his fortune on databases. And Larry Ellison is in particular actually the most interesting person of all these people because he sort of has like an extravagant lifestyle, right? He owns a super yacht. It's not the world's largest yacht, but at least it's in the top 10. He owns his own Hawaiian island. Right? I'm not making this up, right? The one that I boxed here, like he doesn't own a small little thing on the side. He owns a big one, right? Lanai. Yeah, it only has like 1,000 people living on it, and a lot of it's uninhabited, but like, again, he owns an island, a Hawaiian island. This is the Oracle Corporation in Silicon Valley. This is the headquarters. It might be hard to see from the back, but they essentially build all the buildings that look like database disks, right? That's amazing. And then I think sort of goes without saying, he has had many wives. He's had many girlfriends. So this is his current girlfriend of an undeterminate age, but clearly she's at least 2x younger than he is, right? So why did I bring all this up, right? Databases are an interesting problem. Databases are interesting systems, and you can make a lot of money with them, right? Now, back in reality for us, to help you motivate why you should take this course, I would say that for us in the real world, database systems are, database developers are still in demand a lot, and people are willing to pay a lot of money to get people that know how to work on database system internals. Not just at the major corporations, but also there's a lot of database startups, both in Silicon Valley and other places, because there's a lot of still unsolved problems with data management and data processing, especially when you're trying to do it at scale or super high throughputs. So I can't prove this, but is my conjecture that it is my opinion that when I talk to people that are hiring tech recruiters and things like that, if you're able to work on the internals of a database management system, then you have enough sort of technical skills that you're likely going to be able to successfully write code in any other part of computer science, right? So if you can working on a database system is like working on an operating system or like an embedded system. It's really hard to get it to work both correctly and efficiently. So the same skills that you can apply from making a single node database system work, you can then apply to other facets of tech, right? It doesn't work the other way though. Like if you're like a good JavaScript developer, no one's going to hire you to work on the internals of a database system, right? So that's why you should take this class. This class is going to give you a hands-on experience working on a state-of-the-art database system. We're going to cover state-of-the-art topics. And at the end, the goal is that you should be proficient in working on a database management system. And whether you continue with that when you leave CMU, it doesn't matter. I think there'll be lessons you'll learn through this course that'll serve you well the rest of your life. All right, so for today's agenda, I first want to discuss the wait list, get that out of the way, because we're kind of standing room only at this point. Then we're going to spend time talking about what the course outline actually is going to be like. And then I always like to spend the second half of the first lecture giving everyone a crash course on the history of databases. Right? How do we lead up to the point we're at today when we're going to start talking about these modern systems? All right, so the wait list. When I checked this morning, there's 53 people on the wait list. And the max capacity for this course is unfortunately at 40 people. And this is a byproduct of the amount of time that I have, the amount of resources we have for you guys to use, and in fact, we only have one TA. So when I checked this morning, there's currently 3 free slots that we have available in the course. So we're going to take 3 people off the waiting list. So there's some politics involved in how we selected people on the wait list before the course started, which is above my pay grade, so I don't really understand how that works. But now, at this point, I'm free to select who I want. And so what we're going to do is we're going to pull people off the waiting list in the order that you complete project number 1. So I'll announce project number 1 on Thursday, and that way everyone sort of has knowledge of this is coming out, so that no one gets a head start or whatever. And we'll all release it at the same time, and everyone has the same amount of time to finish it. And if you pass all of the test cases and your code works 100%, I will pick people off the waiting list in that order. Okay? So any questions about that? Okay, cool. All right. And so again, I'll announce what the project is next week, or on Thursday. All right, so again, for this course is not like an undergrad introduction to database systems. I'm going to assume that you already know how relational database systems work at a high level. So now we're going to get into actually the nitty-gritty details of how do you build a modern system. And so in the end, you're going to be proficient at writing code that's both correct, because that's a big deal in databases, right? If you store data and then you come back and try to read that same data and it comes back wrong, people get upset, right? Because you end up losing money, right? If your bank account all of a sudden starts, going down for an unknown reason, that's bad. So we need to make sure that our system we build is correct. And then we also need to make sure that it's performant. It means it can work efficiently on the modern resources that we have available to us. So that means a lot of cores and a lot of RAM. So we're also going to teach you how to do sort of proper documentation, how to write test cases. All the projects you'll do, at least actually for project number 3, you'll be required to do code reviews with each other, right? So we're sort of try to teach you how to do high quality engineering here in academia, so that when you go out in the real world, people don't surprise you when say, do a code review and you don't know what they're talking about. And you're also going to get proficient at working on a large code base that has a bunch of code that you didn't write. And this is actually important because this is when I go talk to people in industry and I say, hey, look, I'm teaching this course on database system internals. What's the one skill that you want a student that goes through the course to know how to do when they come out of it? Do you want them to know how to do latch-free data structures? You want them to know how to do recovery, right? And they all say the same thing. They all say that they want a student that is capable of working on a large code base independently. Right? And it means that you can look at the code and figure out what's going on without having to go, bother everyone over and over again, right? And the reason why this matters is because if you're smart enough to work on a large code base independently, then it doesn't matter what they're trying to get you to do in their database system. You should be able to plop down and complete it, right? And so this is why we're doing code reviews and other things, and why we're going to use a real database system for all our projects, is because this will give you exposure to a large amount of code that you didn't write. Because it's very unlikely that you're going to go off, when you graduate from CMU, go start a new job, and they're going to say, hey, look, write the system from scratch. Right? That doesn't happen anymore. Even if if it's a brand new project or a greenfield project, like you're going to have libraries and other things you're going to pull in that you're going to want to use that you're not going to write yourself. So being able to do this, again, it's not something I can teach you. Just the more practice you get, the better you'll get. All right. So for this class, all the course topics, all the things we're going to discuss are going to be in the context of single node in-memory database management systems. So that means two things. So one, we're going to sort of throw away a lot of the stuff we talked about in the intro class about disk-based systems like buffer pools and things like that. And we're going to focus on database systems that assume that the primary source location of the database is entirely in main memory. Because it's going to allow you to do certain things that go much faster than you could in a traditional legacy disk-based system. We're also going to ignore distributed computing problems or distributed systems problems because 99% of the people, 99% of the databases out there don't need to run on multiple machines. Yes, there's always the Facebooks and the Googles and the Amazons and Microsofts of the world. Right? Those guys are outliers. Most people, if you just have enough RAM and enough cores, this is good enough. So this is why we're going to focus on this. And we're also only going to cover state-of-the-art topics, meaning we're going to discuss papers and other things that have come out in the last 5 or 10 years. The paper you'll read on Thursday is actually from 1992, but it's a good summary of what we're actually trying to do. But going beyond that, we're always going to focus on sort of the newer techniques. So this is not a course on classical database systems. I'll assume you've sort of absorbed that or learned about that from an intro class. So the topics we're going to cover, I sort of like to break it down in sort of 2 parts, right? The first part is like, here's the basic things or the fundamental components you need to have if you're building a new database system. Things like a hierarchical control, indexes, recovery, right? And then once we sort of cover all that, then we'll spend time talking about here's the nice things you need to have or want to have in a modern system. So things like vectorization, compilation, using new storage hardware like non-volatile memory, things like that. So the first part will sort of focus, say, here's how you build a system and have sort of the basic groundwork, what you need to say, here's a new database system that you want people to use. And then the second part is, here's the extra steps now to make it go even faster than what you had before. So again, for the background of this course, I'm going to assume that you've already taken either the intro course, 15.415 or 15.615 here at CMU last fall, or you've taken a database course, some point in the past. And so that, because I'm not going to spend time covering sort of basic database things. So I'm not going to cover SQL. I'm going to assume you know that. I'm not going to cover serializable theory, right? So I'm not going to cover isolation levels or anomalies. You should all know what those things mean. I'm not going to cover relational algebra. I'm not going to cover basic algorithms and data structures and indexes, right? So I'll discuss like at a high level, here's here's how they did it in the past in the 1970s and 80s, but here's actually how we do it today. So you sort of need to understand what's been done before that was covered in the intro course in order to understand why we're doing the things to make it go faster in the newer course, or in this new course. Okay? So if you're uncomfortable with serializability, or both complex serializability and view serializability, then it may not be the right course for you. Okay? So now all the projects in this class will be entirely on C++11. So if you don't know C++11, if it's not hard to pick up. If you know C or C++99, then you can pick it up as you go along. But you should be prepared to be able to debug, profile, and test a multi-threaded program for all these projects. Right? So debugging means what? Running in GDB. Profiling means it runs in valgrind, callgrind, or memcheck, or perf. And then be able to write test cases. We use gtest for all the testing frameworks, so we'll have sort of thing set up for you already, but you have to be able to write your own test cases to expand what we already have to test the things that you're actually trying to implement. Okay? All right, so the course logistics are all available on the website, so it'll be the course policies and the schedule. The schedule might get tweaked as we go along. I'll either add or drop papers when we decide, is there a certain area that I think we need to cover more. I'm a strict adherent to CMU's academic policy for honesty and plagiarism. If you don't know what that is, then go to that link there and see what it's all about. I don't care what you did as an undergrad or how the rules were at your other school. CMU is actually being very strict this year about plagiarism and other things, so don't try to mess around with it. If you're not sure whether you're doing the right thing, meaning like say you find some code on Stack Exchange and you want to use it in your project, and you don't know what's the right, whether that's okay or not, please email me and discuss it first, because I'd rather have you say, hey, look, is this the right thing to do, and we can figure out whether that's okay or not, than me find out later on that you did something that you shouldn't have done, and then I have to go report you to Warner Hall, right? Because it's a waste of my time and it's a waste of your time, because you will have to fail the course. So I'm serious. Please don't plagiarize. Please don't steal things that you didn't do, and don't try to pass it off as your own, because I will take it seriously. All right. So for office hours, it'll be immediately after every class on Tuesday and Thursday in my office on the 9th floor on Gates here. The things that we can come talk about, if you want to talk to me about, we can talk about the projects, how your implementation is going. We can talk about the papers we're discussing, if there's any clarifications or questions you may have about what they actually mean. And I put this every year, and believe it or not, people actually do take me up on this offer. If you're having trouble with your girlfriend or boyfriend or whatever, you can come talk to me, and I would try to give you my advice. We all laugh, but believe it or not, people, the reason I put this up is because in the past, before I said, yes, I'll talk about your relationship problems, people just come and share their problems with me, right? And I guess I help them, I don't know. So again, if you want to do this, I can help out. Okay, the head TA, I guess the only TA for this course is Dana Van Aken, seated over there. Dana is awesome. Dana is a third-year PhD student here in the CS department. She just got back from her 2016 MSR internship, which is a big deal to get. And she's also a 2016 NSF graduate fellowship winner, which is very prestigious and very difficult to get. So she won that last year. So Dana is probably smarter than I am. Actually, I know she's smarter than I am. But the key thing is that she doesn't know it yet. And by the time she figures it out, she'll graduate, we'll kick her out, right? So she'll be helping us out with the projects and other things like that. So if you have any questions, you can talk to her. All right, so the things you're going to be graded on this course is comprised of 3 things plus an extra credit. So I'll go through each of these one by one. So the first is that we have these daily reading assignments for every class. So if you look on the schedule, you'll see that I've listed a bunch of papers for each topic we're going to discuss on a lecture. And then one of them will be marked with this circle and a star, and that indicates that it's the mandatory or primary reading for that day. So before every class, you're required to go read that paper and then write a simple synopsis about it. And so this is not meant to be a book report. This is meant to be just to show that you've read the paper and you understand sort of the high-level details about it. So that way, when you show up in the lecture, it's not like you're seeing something for the very first time. We can get past sort of the basic things, and we can focus on the more complex topics. So for the synopsis, it should be basically 5 sentences, a single paragraph. The first 3 sentences should be the high-level overview about what the paper was about, who they are, what they're trying to test, what their experiments were. The second sentence should be what system they're using for the experiments, right? Is it MySQL? Is it MongoDB? Is it Postgres or whatever? And then the last sentence should be sort of a quick blurb about what workloads they used to evaluate the system in their experiments. And this last one's important because when it comes time for you to do your final project in this course, you don't want to sort of scramble to figure out what benchmark am I going to use, what workloads can I use to test the thing I want to test, right? By understanding what all people have done in previous papers, you'll know right away that, oh, I want to be using TPCC or TPCH or YCSB. And the good news is that we have all these benchmarks already written for you, so you don't have to do the boring stuff. All right, I've written TPCC 4 times when I was grad school. You should never have to do that. We've already done it for you, okay? And so what you'll need to do is that there's this link here. It'll take you to a Google form. There'll be a drop-down to select what day you're submitting the synopsis, the reading summary for, and then you put in your Andrew ID and then your single paragraph, right? And then I'll check it later on. And so I'm being very strict about the timing for this. It has to be done at 11:59 a.m. right before the class starts. Because it doesn't make sense for you to write the review after I've already taught the material, because that sort of defeats the whole purpose of this, okay? So again, I hate to have to say this over and over again, but please do not plagiarize. Please do not copy the text from so many other people. I actually do read these things. So make sure you don't, everything's done in your own writing, because it's really for your own benefit. It's not just sort of try to pull fast one past me, right? It's really meant for you to learn this stuff. All right, so now for the programming projects, there'll be 3 projects throughout the entire semester. And they'll all be done in the context of the new database management system we're building here at CMU called Peloton. So Peloton is an in-memory hybrid database management system. So hybrid means that it can do fast transactions and analytics all inside a single system. This is a modern code base written all in C++ 11 and it's multi-threaded. And the good news is that it's open source and Apache license. So when we did all these projects last year, the current version of the system still had sort of the top half of Postgres. So the way everyone always builds a new database system, you take Postgres, you rip out the bottom half because that part's slow, and you rewrite all those things. But then you keep the top half because that gives you like the SQL support, the networking layer, the configuration files, catalogs, and things like that. So this worked fine up until about 6 or 7 months ago, and then we realized, oh, well, the top half part is actually really slow too. So we ripped all that out as well. So everything is now written from scratch. We do speak the Postgres wire protocol. That means you can open up with pSQL in the terminal on the command line and test it. It works in JDBC. But there'll be some facets of SQL that we don't fully support. So, but for everything you need to do in this class, that won't be a problem. So I'll discuss more about how to get started with the first project next class. I'll show you how to download the source code, how to get it running on your laptop and everything. And you should be able to get this up and running pretty easily. We've done this enough times, and enough people have gone through the process that we have instructions and everything for how you're going to do everything. All right. So for the first couple of projects, you'll be able to do this on. Actually, first 2 projects, you'll be able to do this on your laptop. Do all the development there, and then when it comes time for actually doing more thorough testing and benchmarking, we do have a small cluster of machines that was donated to us by MemSQL and Micron that you can log into and do sort of more thorough testing. So these machines have I think 2 sockets, 6 cores apiece, so 12 real cores and 24 with hyperthreading, and then 128 gigs of RAM apiece. Right, so these are much more powerful than you have in your laptop, and you do more thorough testing with them. So Peloton currently only builds on Linux. I did have somebody, he was bored and they got it to compile on Windows 10 with the new Ubuntu libc stuff, but I don't recommend that. So we haven't tried to test it on a Mac. I don't have a Mac to do this. It may work, we just don't know. But we'll provide you with a Vagrant configuration file that'll download the VM automatically and set it up, and you can do all your development in there, right? So again, we've done everything for you. It should be really easy to get up and running with this. All right, so for the first 2 projects, they're going to be, everyone's going to have to implement the same thing. So what we'll do is the first project will be done individually, right? And then the second project, you'll get together in groups of 3, at most 3, and you'll implement those together. And then for the third project, you probably end up being the same group you do for project 2, and you guys will just pick a project that you want to do, right? So the first 2 projects will be done with exactly sort of the setup we tell you to do, and the third one you'll pick on your own. So again, if you have 40 people in the class, we'll have roughly about 13 groups of 3, and we may adjust that as we go along. And again, for these projects, please don't steal code from other people. Everything's being done on GitHub, so yes, you can go snoop at other people's in the class and see their source code. That doesn't help you. We will run the Stanford code checker to make sure that it is actually your own code. So please don't plagiarize and don't borrow things from other people, okay? Because then again, I will have to fail you. All right, so the third project I talked about a little bit is in your groups of 3, you'll pick some project on some topic that you want to do that's relevant to the things that we discussed in the course. And then you'll propose it in the class. I'll say, yes, go ahead and do this. And then you'll have, I think, a month and a half or 2 months to actually implement it inside of Peloton. And the idea here is that you actually want to write something that is useful and it solves a real problem. And then the goal is to actually get it merged into the full system. So we had roughly about 7 out of 10 groups last semester or last year had their projects actually be good enough and working working fast enough that actually we got merged into the full system. So for this, you don't have to worry about picking a topic just yet. We'll take care of it after you come back from spring break in March. And then if you don't know what you want to do, I'll provide a bunch of sample topics of things that I think are interesting that you could work on. And again, if there's something, if you're a PhD student or a master's student doing research in some other area, and there's something you want to apply from that project into our system, by all means, that sounds awesome too, okay? So for project 3, for the first 2 projects, you just turn in the source code, and we run it to see whether you pass all the tests. For project 3, it's actually a bit more, you have to turn in more stuff because we want to get this thing into the full system. So the first thing you'll have is a proposal, and they'll present those in class. And then there'll be a project update near the end of the semester to say what the status is of what you're doing. And then for the final turn-in, there'll be some code reviews. There'll be a final presentation on the final exam day. And then there'll be the code drop when we actually want to merge the code into the master branch. So the proposal will just be a 5-minute overview about what you plan on doing, and you'll discuss what files you want to modify, how you think you're actually going to make this thing work, and test it. And I'll cover this as we get closer to the proposal date. But it's basically you want to show up and say, here's what we're doing, and here's why we think we're capable of doing this. And we've thought about this enough where we know where in the code we need to change things. For the status update, it's sort of the same thing. You just give an update to everyone else, let you know where you're at in the system. What are some problems you maybe encountered and how you solve them? And the idea here is sort of have this be a collaborative thing, because if there's some wonky piece of the system that you had to go fix, there may be another group that has the same problem and they'll want to use your code. So we had this last year where some groups started fixing a bunch of bugs in some part of the system that was not really thoroughly tested, and we were sending patches between amongst the different groups, right? And it's not, again, you just go in the silo, you go in the bunker and write this code yourself. We're trying to all do this together and do a good job, because that's how it's going to be when you go out in the real world. All right, so the other big thing that we're doing this semester that was successful last time is that we're doing code reviews. So what will happen is I'll pair off different groups at different times in the semester, at least 2 times, and you'll have to look at their project code and try to understand what they're trying to do and give feedback about what you think of the quality what you think of their quality of the code. And the idea here is that we want to catch early on if there's some assumption you're making or some mistake you're making. We want to catch that early on rather than have it be 5 days before the deadline. You realize everything you did for the last month was a total waste of time. So these code reviews are very common out in the real world, and the idea is, again, by looking at how other people write their code, it makes you a better programmer as well, and it allows you to discern whether your code is actually good enough as well, because you see what other people have done. So I'll pair you off in groups as we go along, and I'll announce how the protocol will be. And it turns out GitHub actually updated their API for doing code reviews on the website, and it actually it's gotten much better in the last year. So we're going to use GitHub for everything. And the grading for this will be based on participation. So everyone will have a public account, and then Dana and I can go and see what the code review comments are from one group to the next, and then go check to see whether you actually address those issues. And then for the final presentation, it'll be on we'll when we had the scheduled exam, it was after the reading period. And the idea is here, you come and give a 10-minute presentation to the class about what you did and what your measurements were and what you found. And I'll have pizza and we'll give out t-shirts and things like that. So for this, you want to include any benchmark numbers that you've done to see that your system is actually performing well. Last time we had people doing live demos of certain things. Instead of showing graphs, they would show like, here's the system actually running live. And people always seem to appreciate that. So if you want to do that, I strongly encourage that as well. And again, so then you won't get a grade for the final project until you actually do the code drop. And the code drop means when you're able to merge your code, if we want to, into the full system without any conflicts or any problems. Right, so that means that if your code can merge into the master branch without any issues, then it's considered complete. And so what we'll do is, because every single time we merge new code that may conflict with any changes you made, we'll pick a random order of how people are going to merge their code one by one, and we'll take care of it that way, right? And so for this, for your final code drop, you need to make sure you have you've addressed all the comments and feedback that you got in all the 2 different code reviews. You need to make sure that you write all the test cases to verify that your code is actually working correctly, and make sure that you have good code coverage when you do these tests. And then you want to make sure that you provide documentation both in comments in the source code as well as like README files in the source code directories that explain what your project is actually doing. So that if someone comes along later on and says, what the hell is this project? Who wrote all this code? What's going on? They can look at the READMEs and understand this much easily. Because again, this is how it's going to be when you go out in the real world. And then there'll be a final exam, and the final exam actually will occur before the final code drop. So this will be on the last day of class, and it'll be in this room here. So it's a closed book, it's only an hour and a half, and we'll cover all the topics that we discuss in the course. And it'll be sort of a long form answer essay kind of thing. And I'll provide the sample exam that I gave out last year to give you, as we get closer to the date, so that you can see what's expected for the final exam. And then the last piece, I'll say that there'll be extra credit available for students as we go along. And the idea here is that we are writing an encyclopedia of database systems here at CMU. It's not public yet. But the idea is that you'll pick one database system that you find interesting, and you'll sort of write like a Wikipedia-style article about what it actually does. So you say, here's how they do transactions, here's how they do recovery, here's how they do different kind of query processing techniques and things like that. And the idea is here that you provide citations and attributions for this work, and then we'll make this thing public when we're done. So there's a website that's available that we have set up for this, but I'll talk more about that as we get along later in the semester. And again, I don't have to say this again, but when it comes time to writing your extra credit stuff, please don't plagiarize, because your name will be on it, and it'll be public, and it'll look bad. Okay? All right, so the grade breakdown for the course will be 10% for the reading reviews, 10% for project 1, and then project 2 will be 25%, and 40% for project 3, and the final exam will be 15%. So you can see from this, 75% of the grade is all on the projects. So this is a programming heavy course. Everything's going to be based on the projects here. And then the extra credit, you can get another 10%. There's a Piazza website set up. I think I sent out invites to everyone that was enrolled in the course yesterday. If you didn't get that email, let me know. If you want to audit the course and want to be added to Piazza, please email me and we can do that. If you have any technical questions about the projects as the semester goes along, please use Piazza and don't email me or Dana directly. Because if you have a question about, where does this file do, where's this thing, how do I do this, somebody else may be having the same question. So we're going to make sure that everything's public and other people can see the same things. If there's any sort of non-project related questions, like if you need a medical excuse or things like that, please email me and don't post it on Piazza. Okay? So any questions about what's expected for the course, any questions about the project, or anything like that? Everyone seems okay. Okay. All right, so we have about an hour left. So again, I always like to do the sort of my crash history of databases. So for this, what I'll be talking about is actually comprised of 2 different papers. The first is a paper written by Mike Stonebreaker called "What Goes Around Comes Around," that he wrote as an introduction to the Red Book. The Red Book is the sort of this compendium of different database papers that was selected by Stonebreaker and another professor at Berkeley. But here's the things that we think are actually you should learn if you want to know about database systems. So he has a nice paper that says, here's basically how database systems got started. Here's why some of the ones that don't exist anymore are bad, and here's why the relational model actually won in the end. But this was written in 2006, and this is sort of before the NoSQL guys really took off and the NewSQL guys became more popular. So then the second paper is a paper I wrote last year with industry analysts back in London called What's Really New with NewSQL. And this sort of picks up where they leave off, but focusing on relational and database management systems. We don't really discuss NoSQL, but I'll discuss that in the lecture here. All right, so the interesting thing about database systems is that a lot of the things that we're going to discuss in this class, the problems are not new. So in the 1970s, when they were building the first database systems, a lot of the challenges they had to overcome, with the hardware and how applications were going to use databases, turn out to be applicable still today. And in many cases, we'll see that they came up with an idea of how to do things in the 1970s, but it turned out to be a bad idea for that time, and then they ended up abandoning it. And it wasn't until 30 years later that people would go back and say, oh, well, actually, this is actually a good idea now. We actually can do this. So query compilation is a good example. Doing denormalization of tables is another good example, right? They talked about doing in the first system at IBM, then it turned out to be a bad idea, and then Google comes out 30 years later and says, oh, we're doing this now too. So in particular, I think the SQL versus NoSQL debate, if you want to call it that, is very reminiscent to the relational model versus the codicil model debate from the early 1970s. All right, how many of you actually have heard of codicil? One. Okay, maybe two. Right? So clearly we know who won, because if you know what this one is, but not what this one is, right? This one won, right? So a lot of the arguments that the NoSQL guys make now are basically the same argument that the codicil guys are making in 1972, 1973. And obviously they didn't win because nobody uses them. So a lot of the problems that we're going to face today are not new. What's new is the hardware has changed, the scale of the problem has changed, and therefore the techniques that are available to us have changed. So we'll talk a little bit as we go along in the semester, oh, here's what IBM did, or here's what Ingress did. But we'll talk about, again, we're going to focus on how you actually solve these problems in a modern system. So if we go back until the 1960s, one of the first database systems that came out was this thing called IBM IMS, Information Management System. Who here has heard of IMS? No one. Who here has used IMS? All right. All of you should be raising your hand, because I guarantee at some point in your life you've used IMS. If you've ever taken money out of ATM, if you've ever booked an airline ticket, anytime you deal with an old bank, an old financial firm, I guarantee a lot of them are still running IMS. IMS is still kind of, I don't know what the exact numbers are, but it's still the biggest money makers for IBM. You wouldn't build a new, if you're a new startup, you wouldn't choose IMS, but there's still all these legacy systems that first came online when they first started buying computers and database systems in the 1970s. They went with IMS, and for legacy reasons, they can't get rid of it. So IMS was developed in the 1960s at the behest of NASA to keep track of all of the parts and supplies for the Apollo moon mission. And obviously in the 1960s, this is before NASA was called NASA, but it's still the US government space program. And for this, it has three key aspects of its system design. The first is that it uses a hierarchical data model, right? And I'll explain what that means in the next slide. But in particular, it also uses a programmer-defined storage API. So what that means that, unlike in SQL, when you say create table, you're creating a logical table, and you don't know how the database system is actually going to physically store it. In IMS, you would say, I'm creating this table and I want it to be a B+ tree. Or I'm creating this table and I want it to be a hash table. And what would happen is, based on what data structure you would use, IMS would then expose different API calls that you could use to access the table. But then that means that if you had, say, if I chose to do a B+ tree, I could do range scans. But if I chose to do a hash table, then I couldn't do range scans. So the problem with this is, if you go back and change your mind, you can't just flip a switch and have it go from one data structure to the next. You had to dump the table out and load it back in, right? Which is a big pain. And the other key thing about it is that it didn't support SQL or declarative language like SQL. It supported this query tuple at a time API. So you would literally have to write for loops to go walk through each of these collections of data and make all the API calls yourself. So if you say you need to do a join between two tables, you would write two nested for loops and do the join yourself. This is a bit dated because this is not, this is not as common as it used to be maybe 5 or 6 years ago. Can anybody think of sort of a big data system that sounds sort of like this that people were using a lot? MapReduce and Hadoop, right? This is basically the same thing that they use, right? And of course now nobody uses MapReduce directly. Everyone still goes back to using SQL. So just to show you what the hierarchical data model looks like. So here's a really simple schema where you have suppliers and parts. Again, thinking back to the Apollo Moon mission, it makes sense they'd use a hierarchical model because that was the thing they were keeping track of. They were keeping track of all the the million different parts that you had for whatever the spacecraft, and you wanted to know who was supplying them and how much you had in stock. So for this, you have, say, two collections. You have a supplier and you have a part, and it's hierarchical because this is saying that every part has to be part of a supplier. So when you actually instantiated the database in the hierarchical model, it looks sort of like this. So this looks like we'd expect in a relational model, right? You have a table and it has some tuples. But the difference is that you'd have this sort of extra attribute here that say, here's the parts. And you would have pointers to different data structures for each supplier to say, here's all the parts that they're supplying. Right? So then when you wanted to say, give me all the parts for a particular supplier, you would write a for loop to go through and find the thing you were looking for, and then iterate through all the different parts here. So the problem with this approach is that you have duplicate data, because every single time someone sells a battery, even though it's the same battery, we have to have the duplicate name here. And the other problem is there's no data independence between how you define the logical schema of the database and how it's actually physically stored in the system, right? Remember I said if you declare it as a B+ tree, that gives you a certain API. Declare it as a hash table, it gives you another API. So IMS was sort of, again, one of the first database systems that were invented. Some guy complained to me on my blog once that there was actually another earlier system than IMS that came out before this. I tried to Google and try to find what it actually was, and there's not actually a lot of information. So there may be other systems that came out in the 1960s, but they're kind of sort of lost to time. IMS is the most famous one, and that's actually the one people still use today. So IMS came out in 1968. In the early 1970s, some people that were working on COBOL programs got together and said, well, IMS is nice and all, but when you write IMS database code, it's very specific to IMS. So would it be nice if we had sort of a standard API that we can embed in a language so that no matter whether you're using IBM's system or somebody else's system, you can still make the same sort of database API calls. Sort of similar to how people use JDBC or ODBC today. So some COBOL people got together, and they were led by this guy named Charlie Bachman. And they proposed this thing called CODOSIL, which is, I actually don't know what it stands for, but it was the sort of standard API for how to access the database in COBOL programs. Right, who here has heard of COBOL? All right, very few too still, okay. Again, it's not something if you're doing a startup, you wouldn't want to write COBOL programs, but people actually still do it. So Charlie Bachman is actually, a pretty sharp guy. He's still alive. I think he's like 90. But he won the Turing Award in 1973 for this work for this CODOSIL work here. So this was not sort of a crazy idea, but when we look at it now, it does seem kind of archaic and it seems like a bad idea. All right, so the CODOSIL, you're going to use a network data model, and I'll explain what that is in the next slide. And you're going to still have that same tuple at a time interface that we saw with the hierarchical model in IMS. So if we go back to that same parts and supplier database here, what we see now is we have sort of a bunch of more collections than we had before. So we're still going to have a supplier, and we're still going to have part, but they're going to have this cross-reference collection called supply. But then the thing that would happen in the data model when you would declare these relationships, it would automatically create these cross-reference sets, right? That says supply. So a supplier supplies a supply, and that supply is supplied by a part. Right? So it's sort of the way to read this. And so these things would automatically get created for you. So then, again, if you want to say, give me all the parts that are being supplied by a supplier, you'd have to write a for loop to iterate through all of this and traverse down the network to get this thing, and then you traverse your way back up the other direction, right? And again, it's much more nested for loops. It's very cumbersome to do, so this sort of sucks. So the two problems with the network model are, sort of obvious. The queries are very complex and unnatural. But the second problem is that it was actually very easy to corrupt your database in this model. Because what would happen is, say this cross-reference set here gets destroyed, like the disk head crashes or something, something corrupts the data, then you basically lose the whole thing, because now you have no way of going from this to this, because this thing was telling you how to get there. So again, if you just lose one of these things, the whole thing gets lost. So that sucked. All right, so now in the early 1970s, right around the time the Codicil guys were codifying their standard, there's this guy named Ted Codd at IBM, IBM Research, first in New York, but then later in San Jose. And he was not a computer scientist, right? This is very early before computer science was actually something you get a degree in. So he was this mathematician. He was walking around the IBM office, and he was seeing all these IBM programmers spending their time rewriting IMS and Codicil programs over and over again, right? So anytime the database schema changed, or the layout changed, or something changed, you had to go back and change all your code. Remember I said if you load your table as a B+ tree and realize, oh, I really want a hash table, you then have to dump out the table and load it back in, but then you got to go back and change the code and change all the API calls to make hash table calls instead of B+ tree calls. So this is really a big waste of time, and he saw all these people doing this over and over again. So he proposed this really nice abstraction to avoid all the problems and all the wasted time and money here that people were doing. Now, I understand back to in the 1970s, computers were way more expensive than people, right? So, say you had this one giant, super expensive machine. If you had, 20 people spending their time rewriting code, that wasn't that big of a deal. But nowadays, obviously, people are more expensive than machines, and so if we had to do this now, it would be terrible. So he was sort of prescient in that regard. So he proposed this abstraction called the relational model, and it had three key tenets. The first is that rather than having sort of this hierarchical or network data model, you would just store your database in these simple data structures, relations or tables. And then what would happen is, instead of having to write specific API calls to the database to get data or do things in the database, you would access the data through a high-level language. And of course, when he wrote the paper, he didn't say it was called SQL. That came later. But he proposed that here's this thing, relational algebra, because he was a mathematician, and here's how you actually want to do this. And then the nice thing about it was that it was left up then for the database system to decide how you want to physically store these abstract concepts, these relations. So no longer you had the problem, you actually had to specify, I want a B+ tree or a hash table. The database system could decide, oh, well, your data looks like this, and you want to query it this way. I want to use this data structure. I want to store it in this data model. And it was nice because you're using a high-level language that has no knowledge about how the thing is actually physically stored. You could change the implementation or the actual deployment, how it's actually stored, any way you want, and then the high-level language for your queries doesn't change. So again, if you've taken an Intro to Database course, this should all be very familiar with you, the relational model. So here's that same database we've been talking about. We have the supplier, we have the parts, and then we have a cross-reference table for supplies. And then if you want to get all the parts that are supplied by a particular supplier, we could write a three-way join that would join these things together and produce the answer that we're looking for. Right? So you got to understand, in the 1970s, this is mind-blowing, right? This was sort of controversial. And this is the reason is because of this sort of point here about accessing the data through a high-level language. Nowadays, everyone uses compilers. Nobody writes assembly anymore. But again, back then, compilers were not as good as they are now. So people were saying the idea that a human being, the idea that a compiler will be able to generate a query plan that's more efficient than what a human could write themselves seemed like science fiction. And of course, the database optimizers don't always get the right plan, but most of the time they're pretty good, and they're going to be much better than what a human can actually do. So that part was sort of controversial when it came out, and this is the paper that he wrote in 1970 in the CACM. It's actually not that bad. I mean, it's a bit obtuse because it's more mathematical, and they refer to things that don't make sense for us anymore. Right? Database is spelled with 2 words instead of 1. They refer to things as data banks. But the high-level idea is all there. And it's a short read, so if you're just curious to see what it looks like, you should go take a look. So again, Ted Cobb was a mathematician. He later won the Turing Award for proposing the relational model, but he actually wasn't going to go implement anything. Right? He just wrote this paper, said, "Here's this good idea. I think we should do this," and then left it up to other people to actually implement it. So in the 1970s, some people saw this paper and said, "Wow, I think this is a good idea. Let's actually try to build a system, see if this can work." So the first two systems were System R out of IBM Research in San Jose, and Ingress out of UC Berkeley, that was started by one of my advisors, Mike Stonebreaker. So basically, they were both in Silicon Valley, or at least in San Francisco area, and these two teams were both building the first relational systems. And then Larry Ellison came along a little bit after that, later in the 70s, and started the Oracle project, and sort of following along what these guys were doing. And it turns out, if you talk to the System R guys who are still around, they would say that Larry Ellison would call them on the phone all the time and say, "Hey, look, if you give this input to your database, what output do you get? Like what error codes you get and things like that." And all these guys are just researchers, and they don't know anything about IP or anything like that. So they just tell them, right? And then he would go implement the same thing. So that's sort of how Oracle got started. So again, I'll talk more about Ingress a little bit and System R as we go along. But these are sort of the first two relational database systems that were actually built. IBM never actually commercialized System R. They later came out with DB2, at least almost a decade later after these guys got started. Stonebreaker actually commercialized Ingress. You can still buy it today. Again, if you're doing a startup, I would not use it. But if you're still running it, you still can get a license for it. And of course, Oracle is huge and still there. So that's happened in the 1970s. And then so in the 1980s, it became obvious that the relational model was the correct way to go. So again, the 1970s, it was still going back and forth between codicil and the relational model. And then it sort of became apparent to everyone that the relational model is the correct way to go. So a couple of things happened. IBM came out with DB2 in 1983. And it said, "Hey, look, here's our new relational database management system," and they start selling it. And at the time, IBM was the software behemoth. So whatever they did, people considered that to be the standard. And so that was a big deal when they came out with this. And they announced when DB2 came out that the language they were going to support, the high-level declarative query language they were going to support, was SQL. So the background of SQL was there was this other language that Stonebreaker invented called Quell for Ingress, Quell. The IBM's guys saw that and said, "Oh, we can do it better," and they came out with SQL. So it's the sequel to Quell, sort of play on words, right? So that's why when you see, I always say SQL, people say SQL. It's because when it first came out, it was spelt like this, right? Some people say SQL, but that's how I say it. And it wasn't until like in late 1980s when they came out with a language standard for ANSI and then the international organization that they shortened it just to be SQL. Right? Now it stands for the structured query language, but back then it was the sequel to Quell. Stonebreaker claims Quell was always better, but I've seen it and it's terrible. All right, but don't tell them that. Okay. So a couple things happened now as well. When IBM came out with their system, there was a bunch of new enterprise systems that came out, Informix and Sybase, or sort of other major players. So these four systems were the major ones that came out at the time, and they're all still available. But of course, like Informix got IBM and it's in maintenance mode. Sybase got bought by SAP, and for better or worse, it's in maintenance mode. And then Oracle is still around, and DB2 is still around. So Oracle ended up winning the marketplace because when IBM came out and said, "Hey, here's a new relational database system, and we support SQL," because they were following along what IBM was doing, they supported SQL. So when IBM came out and says, "Here it is, we have a SQL database," Oracle was right there and said, "We're ready. We already support SQL. Use it," right? Whereas Ingress was using Quell, and they later had to add SQL. But some people claim that caused them to lose the marketplace, but that's up for debate. So Ingress sort of was going along. Then Stonebreaker left the company, went back to Berkeley, and then he started Postgres, right? And if you ever want to know what Postgres means, right, it's post-Ingress. That's why it's called Postgres, right? So he started the Postgres project, and that's still around today. All right, so another thing that happened, another trend in the 1980s, later in the 1980s, early 1990s, is that there was these new types of object-oriented databases. So remember, the 1980s is when C++ came out, Smalltalk came out, and this is when people are, writing, C-style programs sucks. Object-oriented is the way to go. So there's a bunch of guys came along and said, "Oh, well, actually writing object-oriented code and storing data in a relational database is a bad idea. What you really want to be able to do is store objects. So then you can have your C++ code immediately write out the object to the database. So there was a bunch of these object-oriented databases that came around in late 80s, early 90s. I actually can't name any of them. They might still exist, but no one would ever use them. These things never actually really took off because there was never a standard language like SQL that you could just use to query them. All these different object-oriented databases had their own API or their own special programming language for writing to them. So it was very hard to get people to adopt them. But what's notable is that a lot of the ideas and technologies that were used in the object-oriented databases actually now exist in the relational databases when they added support for JSON and XML. Right? An object-oriented database is just a JSON database. It's the same thing. There's not really anything new. So here's how it would look like. So let's say you have an application code, whether it's Python or C, it doesn't matter, and you have some object for a student. They have an ID, a name, an email, and then an array of phone numbers. So how you would actually implement this in a relational model is you would have to have two separate tables, right? Because the SQL standard says you can't have array types, although some systems allow you to do that. So you'd have the student table, and then you have a student phone cross-reference table. And so now if you want to do a lookup and say, well, for a particular student, give me their name and all their phone numbers, you would have to do either a join or two separate queries to go get all this information and map it into the object. Right? And this is why the object-oriented guys say relational databases are a bad idea for object-oriented programming, because you have to do all this extra work on the database side of things. So the object-oriented databases guy would say, well, actually, really what you want to do is just take your object and then stick it out into the database and store it directly there. So here I'm showing it in JSON, so this is how you would do this in MongoDB. Right? Of course, now the problem with this is that the queries become complex when you do want to do things beyond just looking up the single record. And there's no standard API for accessing object-oriented JSON or XML data. And so we'll talk a little about the NoSQL guys. For the most part, they're all adding SQL support, except for Mongo. But all the different relational database systems that do support JSON or objects like this all have different function calls or APIs to how to do this. So it's actually not something that's easily transferable from one system to the next. All right, so the 1990s were actually the boring times for the database systems. If you told somebody you're going to go get a PhD in databases in the 1990s, they would be like, why, right? The only real three interesting things that came out around this time were SQL Server got started because Microsoft bought a license to Sybase, got the source code, and went and ported it to work on Windows NT. And when we talk about the Hackathon project, there's one of the authors on that project was the main dude that they hired to work on this. MySQL got started in, I think, in Sweden as a replacement for MSQL. So it's not my as in like my or your. It's my is actually the name of the guy's daughter. This is also the same guy that started MariaDB. Maria is another one of his daughters. So that's where MySQL got started. And then Postgres, the version that came out in the 1980s, again, supported Quell because that's what Stonebreaker wanted or liked to use. But then some grad students at Berkeley got the source code in around 1994, 95, 96, and added support for SQL for it. And then it came out as PostgreSQL. And that's the Postgres everyone knows and uses today. Because at that time, Stonebreaker had abandoned the original Postgres project and had a company called Illustra, which later got bought by Informix. So yeah, so nothing really got exciting. Yes, they added more support for OLAP and analytic queries, but there wasn't any real major game changes during the 1990s. Now, when we get to the 2000s and we have the big internet boom, that's when things start to get interesting. So when all these big internet startups got going, they realized, oh, we need to scale up our database, right? This is getting challenging for us to support all these active users. But the problem was that all of the major database vendors that we've talked about so far, so the Oracles, the IBMs, the Sybase, the Informix, and all those guys, these systems are very, very heavyweight, and they're very expensive, right? So if you now want to scale out and support, 1 million users, you don't want to pay all that, you don't pay a big chunk of your money for Oracle licenses, right? That's not going to work. So the problem, though, the open source databases that we have now were not as robust and full-featured as they are today. So in the early 2000s, like 99, 2000, 2001, MySQL didn't really support transactions because they had this thing MyISAM. Postgres was not the high-quality system that it is today. right? And it's before we get into any of the NoSQL stuff. So what ended up happening is that a lot of these database companies, or not database companies, these internet startup companies end up writing their own custom middleware to take the single node database systems and sort of scale them out manually or do sharding. So Google did this with MySQL. eBay did this with, I think, originally Oracle, right? Because there was no good sort of distributed database or really good scalable database, so they sort of had to write their own application code to manage this for them. Then we get now into the 2000s, and we see the rise of the data warehouses. So these are going to be now, so all the data systems before them were sort of these general purpose systems that were not really good at anything, but you could pretty much do anything you wanted on them. They were not super fast. So then what happened was in the mid-2000s, all these special purpose database systems came out that were designed to do only analytics really, really fast. So you wouldn't want to run your customer, your website, your customer base, or your website on this. You would only use these for do analytics at night or after the fact, after you've already collected the data. So the three key aspects of these systems is that they were distributed and shared nothing. They were all doing relational and SQL. Yes, I know there's like the Hadoop stuff or the MapReduce stuff from Google or Bigtable, but that's sort of as an aside from this. And the downside is that they were all closed source. So the big key thing that came out of this work here is that these systems decided to end up using the decomposition storage model, or the column stores, to get much better performance to do analytics. But obviously you wouldn't want to run transactions on a column store because that would be slow. So the only system that I think that it's still around today, Netezza got bought by IBM, that sort of fizzled out. I think ParExcel might still be around. Or maybe they got bought by Teradata. Data Allegro got bought by Microsoft. Vertica got bought by HP, but then they sold it off last year. And then Greenplum got by EMC, but then they forked it off and made Pivotal. So these systems are still sort of around, some of them, but in some ways, some of them are still really good. Some of them are actually a bit dated. But when they came out, this was a big game changer. Right? In particular, I know, like for Vertica, I had a friend who was like a sales engineer, and he went to go visit an Australian telecom, and they had some query they were running on Oracle that would take days. You plop down Vertica, and it could finish it in minutes. Right? And that was a big game changer. Right? And a lot of that is due because they were doing a column store. Yes?
What's shared nothing?
All right, shared nothing means that when you have, say, a distributed database, each node acts independently and stores some shard or partition of the database. So compare this with shared disk, where everyone writes to the same like shared disk. Compare this with like shared memory, which is everything is running on the same box. Shared nothing just means you don't share anything. All right, so then we get now to the later 2000s, we get the NoSQL systems. And these are systems that are designed for operational workloads, or not transactional, but things that are ingesting data or dealing with customer-facing products. So these guys, oh, that sucks. Because we were here too long? Projector cooling down. Awesome. All right, well, that might just ruin it. I guess we just done. That sucks, because that's going to be on YouTube. All right, so I'm almost done. I'll just finish up. So the NoSQL systems are things like Mongo, Cassandra, HBase, React, Couchbase. So all of these systems, for the most part, when they first came out, declared that they were NoSQL, meaning they thought SQL was slow, the relational model was slow, and therefore they didn't want to support that at all. And now, of course, when you look at, with the exception of MongoDB and some maybe like Redis, they're all now supporting SQL, right? So they said relational model is a bad idea, but it turns out they were wrong, and they're now adding back support for SQL. The key thing about them, though, the way that they got better performance over the relational systems is that they did not support ACID transactions. So in a relational system, a traditional relational system, you could do transactions and have, you do some write and know it be durable. But in these other systems would not allow you to do multi-write transactions. Most famously, MongoDB, when it first came out, they would get these amazing benchmark numbers because they would not actually do writes when you ask them to do a write. So when you write something to Mongo in the early versions, it would immediately come back and say, I got it. But it was just sitting in memory as a buffer. It never actually wrote to the database. So if you wanted to know whether your write was actually successful, you have to go back and ask it a second time and say, that write I just did that actually make it out the disk? And it would tell you whether yes or no. Let's see if this works. Yes. Okay. So the other thing that's interesting about these guys is that, again, they would have all these sort of standard custom APIs, and they would not use SQL, but now they do. But the nice thing about the NoSQL systems is that, for the most part, as far as I know, with the exception of maybe Amazon DynamoDB, they're all open source. Oh, and I guess also Oracle NoSQL, right? So when I showed the data warehouse guys, for the most part, they were all closed source. Some of them are open source now, like Greenplum, but they were all sort of proprietary when they first came out. But the NoSQL guys, when they got started, was like, oh, we're going to support NoSQL or be open source out of the box, which I thought that was kind of nice. Oh, no. And then, so now in the 2010s, we get to the new SQL systems. That doesn't look good too, because there's gonna be this video on YouTube, and it's like, yeah, CMU is this great school, but like our projector sucks, right? All right. So in the 2010s, then we get the rise of these new SQL systems, and so a new SQL system, how it's defined in Wikipedia is that it's a relational database management system that's designed to get the same for OLTP workloads, transactional workloads that can get you the same performance of a NoSQL system without giving up ACID, right? Again, this is what Wikipedia says. I wrote it, so I guess it must be correct, but we can go with that. So they're all relational, they all export SQL. For the most part, they're all distributed. And unfortunately, a lot of them are closed source. So HStore was the system that I helped write when I was in grad school, and it was later commercialized as VoltDB. Those two are open source, but actually for all of these then, except for those two, they're all closed source. This is actually Pivotal Gemfire, which they got rid of, and DB Shards might have just got bought. Well, these are a lot of the systems we'll discuss as we go along. In particular, Hyper is an interesting one out of Germany, and we'll read a lot of papers from those guys. And this is actually the Google Spanner logo. I gave a talk at Google once, and I couldn't find the Google Spanner logo online, so I sort of made my own. I took the Google logo and put the text Spanner underneath it. And afterwards, they came up to like, you can't do that. They got really upset. So this is actually the real Spanner logo. But of course, like you look at this and you don't know what it is, right? So the big trend that's occurring now in the late 2010s is these rise of the hybrid systems, or HTAP systems. So HTAP stands for Hybrid Transactional Analytical Processing. It's sort of a buzzword, but it nicely encapsulates a lot of the things that we'll be talking about during the semester. And the idea is that rather than having a separate data warehouse for your analytics or OLAP and a separate system for OLTP, you can have a single system that can do fast transactions like you can in a new SQL system, but also do complex analytical queries like you do in a data warehouse, all in the context of a single database instance. And so these are mostly distributed and shared nothing. These are going to support relational and SQL. And then it's mixed about which ones are closed source versus open source. So Splice Machine is actually founded by CMU alum. That's open source. Snappy is a combination of Spark and Gemfire, that's open source, and then our system Peloton is open source. MemSQL and Hyper are actually considered to be two of the most state-of-the-art systems in the world today, and we'll discuss a lot about them in the class, and unfortunately those guys are proprietary. So this is where I think the big trend is people are going today. For operational reasons, it's expensive to have to maintain two separate database systems and make sure that they're always working. And so if you can have a system that can still do all the fast transactions you want to do in a new SQL system, but without having to spin up a whole nother Spark cluster or something else to do analytics, that's a nice thing to have. And I think that's where a lot of people are going. You're still going to want your giant data warehouse to collect different OLTP silos. So say, for example, like in Zynga has a bunch of different games, and they're all sort of these front-end OLTP systems, but then you want to combine the different game data into a single giant data warehouse and do a bunch of analytics on there. So that model is still going to exist, but these are going to allow you to do some of these things without having to transfer some of these analytical queries without having to transfer the data first. All right, so at the end of every class, I always like to give a parting thoughts, but here's what I think about what we discussed, and here's what actually the main takeaway should be. I would say in the context of database systems, unlike different fields in computer science, there's a lot of innovations being done at both industry and academia. And industry is not only just the major companies like the Oracles and Microsofts of the world, but there's a lot of startups that are doing some really cool things as well. And unfortunately, they don't publish papers, but there's blog posts and other things I'll bring up as we go along to say, here's what they actually do, and here's why I think it's cool. A lot of the ideas start actually in academia. But what happens is people build sort of small prototypes to test these ideas out, And it's not until a sort of major company picks those ideas up and actually implement them before they actually get combined in a real system. I consider IBM to be the vanguard of database systems from the 1970s and 1980s. Certainly the System R project was very, very influential and set the, sort of set the tone of how you actually build a relational database system. But now I consider actually Google to be sort of one of the state-of-the-art people. Not everything they do is always the best, but they seem to always get the most traction, the most eyeballs for what they're actually doing. Like everyone knows what Spanner does, everyone knows what F1 is, everyone knows Mesa and all these other things. But again, so we won't read actually a lot of Google papers because I think there's ideas, the ideas of what they implement in their systems come from other papers we'll read. In the case of Oracle, they pretty much borrow ideas from anybody that they want, right? And they're usually 4 to 5 years behind the state of the art. I don't mean this in a derogatory way, right? When you think about what the Oracle system actually is used, who actually uses Oracle, it's the most widely deployed database system. So you don't want just sort of random features and things added in it because that might break something for somebody else. They have a very thorough testing process anytime they have a new version because you want to make sure that for anybody it does not cause a problem. And so again, for that reason, part of the success is also related to their slowness, right? So again, the main takeaway too, also from this history, is that the relational model clearly won. The relational model is the right way to go for operational databases when you have sort of transactions and when you ingest data. For more complex things like machine learning and stuff like that, the relational model may not be the right way to go. You may actually want to use arrays or matrices, but that's another topic. Okay. So any questions about this? All right. So again, so we'll start the lecture on Thursday. We're discussing the disk versus in-memory database management systems. I'll also present how you actually want to get started on project number 1. And then a reminder, there'll be a paper. If you go to the website on the schedule, you'll see that there's a paper marked as required reading for Thursday. So make sure your first reading review is submitted before class starts on Thursday. Okay? Awesome, guys. See you Thursday.